Normalized wave function in momentum space of a particle in one dimension is phi p. Here the question has incorrectly written the wave function is normalized. So let us first normalize the wave function. Let us normalize the given wave function using normalization condition. It is phi p equals to a square minus infinity to infinity alpha square p square plus beta square dp is equals to 1 implies a square alpha square pi by 2 beta q equals to 1 or a is equals to 2 beta cube by alpha square pi की power 1 by 2. Here we have used minus infinity to infinity alpha square dp p square plus beta square equals to alpha square pi 2 beta cube. The expectation value delta x is given by x is equals to phi p x phi p which is equals to phi p I cross del by del p into phi p equals to I cross phi p del phi p is equals to I cross a square minus infinity to infinity to alpha square p divided by p square plus beta square का whole square dp equals to 0. Since this function is odd, that's why the value of this integral is 0, where we have used the property which I said it earlier, minus infinity to infinity f of x dx is equals to 0 fx is equals to odd and 2 integral f of x dx if fx is even. Now similarly the expectation value of del x square is given by x square phi p x square phi p equals to minus h square phi p del square p square equals to minus h square a square integral infinity to infinity to alpha square p square plus beta square cube dp plus 8 alpha square minus infinity to infinity p square dp divided by p square plus beta square की power 4 that is equals to minus h square a square minus 2 alpha square 3 pi 8 beta की power 5 plus 8 pi alpha square 16 beta की power 5 equals to minus h square a square minus alpha square pi square by 4 beta की power 5 which is equals to del x square h square alpha square pi की power 4 beta की power 5 into 2 beta cube divided by alpha square pi. Here I made a mistake. Okay, now it is equals to alpha square to 2 h square by beta square del x is equals to x square minus x whole square equals to h square by 2 beta square minus 0, so delta x is equals to h cross by root 2 beta. Now we can solve this problem using dimensional analysis. So let us check it how. That is shortcut for this problem. So if p and p square is added up to beta, that means beta is having dimension of p. Delta x is equals to h cross by p, that means h cross by beta. So any option in which we are getting h cross by beta, that would be our option. Here beta square, beta cube, beta की power 3 by 2, so option C is correct answer using this dimensional analysis. The normalized wave function of a particle in 3 dimension is given by psi r theta phi 1 by root 8 pi a cube e की power minus r by 2a, where a is greater than 0 is a constant. The ratio of most probable distance from the origin to the mean average means RMP to average R का ratio. We have to determine the ratio of RMP to the average R or mean distance. Now we have psi r theta phi is equals to 1 by root 8 pi a cube e की power minus r by 2a are greater than a. The most probable distance is obtained as PR dr mod psi square 4 pi r square dr equals to 1 by 8 pi a cube 4 pi r square e की power minus r by a dr. So pr equals to 1 by 2a cube r square e की power r minus a, or del p by del r by del r is equals to 0 implies 1 by 2a cube 2r minus r square by a r by a equals to 0. Since e power minus r by a cannot be 0 as it makes psi equals to 0, so 2r minus r square by a must be equals to 0 implies r is equals to 2a. The mean distance from origin is given by average r is equals to psi r psi equals to 1 by 8 pi a cube 0 to infinity r e की power minus r by a 4 pi r square dr is equals to 1 by 2a cube r cube e की power minus r by a 0 to infinity dr. Let us evaluate this value of this integral. We are going to write an standard result e की power minus alpha x की power n dx is written as t n plus 1 alpha की power n plus 1. So here we would be having it comparing with this relation r cube e की power minus 1 by a r dr. So we can take it alpha as 1 by a n equals to 3. So the result for r cube e की power minus r by a dr is turning out to be 3 plus 1 divided by a 1 by a की power 3 plus 1, that means a की power 4 into 3 factorial. So our average r become 1 by 2a cube into a की power 4 3 factorial, that means 3a. Thus the ratio of most probable distance from origin to the mean distance from origin is given by RMP by average R equals to 2a by 3a. So answer is 2 by 3. Thus, our correct answer for this problem is option D, 2/3. The state vector of a one-dimensional simple harmonic oscillator of angular frequency omega at time t is equals to 0 is given by psi 0 is given by we have where 0 and 2 are normalized ground state and second excited state. 0 and 2 are ground and second excited state. The minimum time t after which psi t becomes orthogonal to psi 0. That means psi 0 must be equals to 0. Condition of orthogonality. Wave function particle at time t is given by psi t equals to 1 by root 2 0 e की power minus I e0 t by h cut plus 2 minus I e2 t by h cut, that is psi. Applying orthogonality condition. To determine minimum time. We have psi t equals to 0 into psi t equals to t equals to 1 by 2 0 0 e की power minus e 0 2 by h cut plus 2 2 e की power minus I e2 t by h cut is equals to 0, or e की power minus I e0 t by h cut plus I e1 t by h cut is equals to 0 implies e to the power minus I e0 t by h cut is to minus e की power minus I e2 t by h cut, or e to the power I e2 minus e0 by h cut t is equals to minus 1 equals to I pi, or t is equals to pi h cross by e2 minus e0 to pi h cut. e2 is 5 by 2 h cross omega minus e0 is 1 by 2 h cross omega pi h cut by 2 at omega is equals to pi by 2 omega. For a particle in 1D, En is equals to n plus half h cut omega. So E0 is equals to half h cut omega and E2 is equals to 2 plus half h cut omega equals to 5 by 2 h cut omega. So our option here would be pi by 2 omega, option A. A phase shift of 30 degree is observed when a beam of particle of energy 1 MeV is scattered by a target. When the beam energy is changed, the observed phase shift is 60 degree. Assuming that only S-wave scattering is relevant and the cross section does not change with energy, the beam energy is. So in this question we have to determine the beam energy. Here from question we have delta 1 is equals to 30 degree and E1 is equals to 0.1 MeV. Delta 2 is equals to 60 degree. We have to determine E2. Now, the cross section for S-wave scattering is given by sigma S square is equals to 4 pi square K square sin square delta L, implies K square is equals to 4 pi square sigma square sin square delta L. Further, we can check it. The cross sectional does not change with the beam energy. Means sigma 1 theta is equals to sigma 2. Cross section does not change, so that means sigma 1 is equals to sigma 2 as well. Now, we know it. E square by h cross square into 2m equals to 4 pi square sigma square sin square delta L, or plus E square equals to 4 pi square h cross square by twice m into sin square delta L. Here we have used h cross square k square by 2m is equals to E, implies k square is equals to 2m by h cross square E. So this is energy dependence upon sigma and sin delta. So for particle 1, thus the ratio of the energy beam corresponding to different phase shift is E square, not E, it's just E, not E square, it's just E, equals to 4 pi h cross square by twice m to sin square delta n 1 by sigma 1 equals to E2 equals to 4 pi h cross square by twice m to sin square delta L. 2 by sigma 2 implies E1 by E2 is equals to sigma 2 by sigma 1 sin square delta L1 by sin square delta L2. Further, sigma 2 and sigma 1 are equal, so we would be having it E2 is equals to E1 into sin square delta L2 by sin square delta L1. Substituting the values of delta and E1, we get 0.1 MeV sin square 60 degree divided by sin square 30 degree equals to 0.1 MeV into root 3 by 2 square divided by 1 by 2 square equals to, so E2 is equals to 0.3 MeV. Thus, our correct answer would be 0.3 MeV, option 2 or option B. Consider an element U5 of the group SU2 where phi is any one of the parameter of the group. Under an infinitesimally changed phi plus delta phi is changed to U phi plus delta U phi 1 plus X phi into U phi. So, to order delta phi, the matrix X delta phi should always be. So, we have to check it under what condition this condition is true. So, according to question, when phi changes to phi plus del phi, element unit U phi changes to U phi plus delta U phi equals to 1 plus X del phi U of phi. So, thus, there is a change in the angle phi due to its rotation, and this would be carried out by operator del by del phi. We know that this operator, the operator X del phi equals to del by del phi is equals to A operator A dagger equals to del by del phi dagger is equals to minus का del by del phi. That means A is anti-Hermitian. That means X delta phi is also anti-Hermitian. Thus, check it our option. Option D is correct for this question. The Hamiltonian of a two-level system is given by h is equals to 1 by 2 h cross omega. Possible initial state in which probability of the system being in that quantum state does not change with time is. So we have to determine the probability for which the quantum state is independent of time. We just have to determine the coefficient of the wave function at t is equals to 0 states. So the Hamiltonian for two-level system as given by the question is 1, 1, 1, minus 1. We can write it down a by 2, a by 2, a by 2 minus a by 2. ठीक है? We have defined cross omega is equals to a. So the eigenvalue and corresponding eigenvector for the given Hamiltonian are obtained as follows. H minus lambda I would be a by 2 minus lambda a by 2 into a by 2 minus lambda is equals to 0 equals to minus a by 2 minus a by 2 into a minus lambda minus a square by 4 is equals to 0 implies minus a square by 4 plus lambda square minus a square by 4 is equals to 0, or lambda square is equals to a square by 2 implies lambda is equals to plus minus a by root 2. Eigenfunction corresponding to eigenvalue lambda is equals to plus a by root 2 is obtained in following manner. H psi equals to lambda psi implies a by 2 minus a by 2 x y equals to a by root 2 x y. Simplify above equation. So we get a by 2 x plus a by 2 y is equals to a by root 2x, a by 2x minus a by 2y equals to a by root 2y. Or this can be written as x plus y is equals to root 2x, and x minus y can be written as root 2y. Solving for x and y, we get x is equals to 1 plus root 2 and y is equals to 1. The eigenvector corresponding to eigenvalue lambda is equals to a by root 2 is psi is equals to plus root 2 1 root 2 1 plus root 2 1 by root 2 equals to n into 1 plus root 2 1 by root 2, where n is normalization constant. Similarly, eigenvector corresponding eigenvalue lambda is equals to minus a by root 2 is and 1 by root 2 minus 1 1 by root 2. Considering eigenvector corresponding to state to eigenvalue lambda is equals to a by root 2 psi is equals to n 1 plus 1 by root 2 1 by root 2 equals to n sin pi by 2 plus sin pi by 4 to sin pi by 4 equals to n 2 sin 3 pi by 8 cos pi by 8 to 2 sin pi by 8 into cos pi by 8 equals to psi 2n cos pi by 8 sin 3 pi by 8 into sin pi by 8. Similarly, when we would try to obtain the eigenvector corresponding to lambda is equals to a minus a by root 2, there would be psi is proportional to turning out to be sin pi by 8. Thus, the probability of the system in the initial state in which quantum state does not change with time is mod psi cos pi by 8 sin pi by 8. So let us check the option. That means our option B is correct. So we can mark up the solution by determining only the first term. Consider a one-dimension infinite square well defined by Vx is equals to this. If perturbation delta Vx is applied, then correction to the energy of first excited state to first order in delta V is nearest to. So we have to determine the first order correction in the first excited state. So the first excited state and its corresponding energies are given by psi 2x root 2 by a sin 2 pi x by a. E2 is 2 square pi square x square by 2 ma square. The particle is subjected to perturbed potential Vx is equals to V0, 0x less than a by 3, 0 otherwise. The correction to the energy of the first excited state is given by A1 is equals to psi 2 x Vp into psi 2 x equals to V0 2 by a 0 to a by 3 sin square x by a dx, which can be written as V0 by a to 0 to a by 3 1 by 2 1 minus cos 4 pi x by a into dx, which is equals to V0 by a 1 by 2 into a by 24 into 8 plus 3 root 3 upon pi. 2 से 2, a से a, we would be having V0 1 by 3 plus 3 root 3 divided by 24 pi is equals to roughly 0.33 V0. So our option would be 0.33 V0. Option D is correct. The energy eigenvalue En of a quantum system in the potential Vx is equals to C x की power 6. For large values of quantum number n varies, this problem is related to WKB approximation. For potential of the form V of x is equals to lambda mod x to the power m Hamiltonian p square by twice m plus lambda mod x to the power m. The energy eigenvalue corresponding to such potential energy eigenvalue dependence on n and lambda r. Em is proportional to lambda की power 2 m plus 2 and n plus half 2m into m plus 2. For given problem here to 6 implies E6 lambda 2 into 6 plus 2 to n plus half 2 into 6 divided by 6 plus 2 implies E6 is proportional to lambda 1 by 4 n plus 1 by 2 12 by 8, that means 3 by 2. So this dependence is correctly predicted in option B. So option B is our correct answer.